So I just want to show this figure to just illustrate why a lot of this stuff with these velocity products we're working on. We have 6 different products, going all the way back to the 80s, various densities and time sampling. And this just shows Helheim, Kengel, Luswak, and Jakobshaven. And you can see the full time series and all of the different data sets. And again, there's probably more than 1,000 files went into making this plot. 1,000 products, each product having multiple files. And this was all generated in a notebook, pulling the data directly from NSIDC. I'm not going to go into stuff quite as complicated as this figure here, but I just wanted to make the point that the tools we're going to demonstrate today are quite powerful and can be used to really access the data quite well. Okay. Can you see my screen?
Yeah, it looks great.
Okay. Do you want to do the introduction stuff?
Yeah. So as Ian mentioned, we're going to go through some advanced analysis today. It's mostly going to be Ian and Zach walking you through that. The goals are to be able to access an NSIDC data set with ICESat-2 data using IcePix, which is kind of a review. We're going to analyze point and raster data together and do some advanced visualizations of multiple data sets. So in all of this, again, it's code that you'll be able to reference later. So feel free to run it in your own book or just to follow along. And don't worry if you fall behind, because it's pretty complex code, but it's all being built upon the tutorial that we presented yesterday and some of the other tutorials that we have seen this week. So it's getting to the advanced stages. Over to you, Ian.
Hey, Ian, can you make it just a bit bigger?
Oh, I'm in presentation mode.
Oh, okay. It's not bad, but there we go. That's awesome. Thank you.
Okay. So again, I'm going to talk about these 2 packages I put together. Only this time we're going to talk about velocity data instead of image data. Everything is derived from much of the work, actually heavy lifting is in the same base class, and these 2 derive from that. So a lot of things will be familiar for those of you who were around this morning. So we're going to go through the same login procedure, and I see some people had problems with this. I can't vouch for it on another machine. It should work on the hub. I did notice there's some quotes around one of the usernames so if you don't put any quotes in your username, just put your username and password, and that should work. And as far as running, if you want to take the code later and run it offline, I strongly recommend you build a Conda environment using the environment file that's included in the binder directory in the repositories, because that is almost guaranteed to work. And the other thing, someone had a TIFF not found or some kind of other error like that. So that is probably, that can be either a secure authentication error, or it can also be a Dask problem. And Dask is nice because it can do parallel operations and do many things at once, but it can give you problems if you get too greedy. In particular, NSIDC only allows I think it's 15 simultaneous connections from a user. And when you access a tile in the file, I don't know what the timeout is, but it doesn't necessarily hang up the line right away. So if you try and do, say, the number of workers be 8, and actually that can sometimes be twice that in threads. But anyway, a large number of workers will actually overuse, have too many simultaneous connections at once, and then one of them will fail. So that's always a bit of a problem. In the behind the scenes code, I think I ratcheted it down to 2, and I've actually done some benchmarking. You don't actually get much better speed by having more workers. So you're actually better off and safer with a smaller number of workers. It even tends to fail more on some images. The byte data, a 512 chunk is smaller than a floating point data, which is 4 times bigger for 512 by 512. And those ones tend to be more robust because I think there's more time between the interactions with NSIDC and the connections get hung up. So if you have problems, it's probably authentication or it's too many workers, and you may have assigned a number of workers somewhere in the notebook, and that's likely to be your problem. So I'm going to go over this part. I'm just going to run this. This is just doing the termini again. And I'm not going to, since we covered that earlier, I'm not going to really go into detail, but it's doing the load here using that VSI curl. And I've just loaded them in here into a dictionary by year. I could have, if I was a more advanced pandas user, I would have made a table and concatenated them all together and had them indexed by year as well. But sometimes I like dictionaries better. But you can see for any one of these pandas things, we can use the plot function, and we can even plot them and change the coordinate system if we want, as we've seen many times already. I'm not going to go into detail what's happening here with the flow lines, because I'm going to come back to that later. Right now, we're just going through a process of generating an overview map. And I'm not going to say anything about this because this is Zach's, which again, I think is basically refresher material or stuff that will be covered later. So, but it's all about using IcePix to pull data. And then here, Tasha put everything on top of one of these IPY leaflet things. So we're going to look at Jakobshaven. We're going to use these flow lines that were actually, a flow line is, if you put a piece of a marker on the ice, it would be the line that it would follow as it flowed out towards the ocean. We're looking at the terminus positions here, and you can see on this little glacier, which would be called Glacier 2 later on, not much retreats occurred. And you can look on Jakobshaven, which is Glacier 1. There you can see the retreat of more than 15 kilometers, which has led to more than doubling or tripling of speed of this glacier over time. So having a raster data set, you often want to actually render more of a plot than just a map. And Dennis Felixson had a paper where he made this nice set of flow lines. For every glacier in Greenland, you can pretty much, every major glacier in Greenland, you can pull up a set of flow lines like this. And he's following good open science protocol and has archived those on Zenodo. And here we're going to use 3 different classes. The GRIMP flow lines is a simple class that just basically reads the shape file and stores the data in simple dictionary forms. Each shape file so these 6 flow lines would be one shape file. So they're organized by glacier number, and then each flow line has an index for that glacier. We're going to use this CMR URLs file, the GRIMP function again, to search the NSIDC catalog. And we're also going to use this nice RBEL series, which is a lot like the image series we saw before. So just so it wasn't a complete black box, I extracted bits of the code from the actual class definition, but it's not going to run here. So basically, I just start out with a dictionary for each flow line that belongs to the glacier. I open up the shape table or the shape file and put it in a variable called shape table. We iterate through that. For each flow line, we start a new flow line. And then I just pull out the X and Y coordinates, which is really all I need for the stuff I'm doing here, and put it in the dictionary. And then I compute the distance along the flow line from the front of the flow line. And then I just save the flow line index by its index. And I'll show a little bit more how that's organized. So here we're actually doing all of that operation using this GRIMP flow lines function. We're just giving it the shapefile name here, and we're pulling the name out just from the file name. They're named 001, 002. There's a much more comprehensive set of flow lines. For the purposes of the tutorial, we only put in 2 here, so you didn't have to keep downloading all the data. And then a lot of this ice really up here is quite slow moving, and we're not really interested in. We're really interested where all the action's going. So one of the features that this flow lines class has is you can just truncate the length of the flow line to 50 kilometers, which is a nice length for plotting. So we'd run that, and we get a dictionary with indexed by glacier number, glacier 1 and glacier 2, and each one of these has one of these flow lines objects. If we now look at what's for a particular glacier we have a dictionary that has the individual flow lines indexed as by their flow line ID. And then if we want to look at what a particular flow line has, all it really has, again, is simple X, Y, and D. And there's various functions. Rather than having to .x, .b, you can actually pull the data back as XY meters for a given index or XY kilometers. Again, for plotting, for doing the math, I prefer meters, but for plotting things, I generally prefer kilometers because it just clutters up the plot a lot less. The first thing we want to do is for the subsequent plots is get a bounding box that reflects the flow lines we've just decided on. So I just set the min to a very large number and the max to a very small number. And we're going to iterate through those flow lines. So for one of the functions or the methods of this class is it can return the bounds for the given flow line. And then there's a merge bounds function, which does some min-max operations. So what we get is a bounding box that covers the full extent of the flow lines with some pad, I think, around it. And the other thing is, I believe both of these files, the glacier ID, the flow line IDs are the same, but we just build a unique list of the actual flow line IDs. So 3, 4, 5, 6, 7, 8. So now we've got a set of flow lines we're ready to work with, but we need some velocity data. So this will look similar to what I showed earlier, and it takes a second to load because it has to get all of the boxes. So I've set it up to do the annual velocities here, which is NSID 725, but we could go to monthly velocities. We could go to, quarterly velocities, monthly velocities, or velocities every 6 to 12 days with the interval depending on whether 1 or 2 Sentinel satellites were flying at the time. We also have the Terrasar velocities, and those are indexed by individual glaciers. So if we're not going to use Joughin 7 here, but if we were, we would be looking for, if they're indexed by latitude inside of the ice sheet. So that would be on the west side of the ice sheet at 69.1. We would select that, and that would pull up all the Joughin 7. And then once we had what we wanted, we would do the search, which has already been done here. Normally, you wouldn't have this thing spitting out up here, but I use verbose equals true to actually spit out the CMR search just so you can see what's going on. So we have this little widget. It returns a product, a date, a product filter, and it just does all the nasty string stuff to put it into a long string like this that you would never want to type by hand. And it sends, when you do the query, and I'll do that manually down here rather than doing it in my code, you can see. I'm actually going to remove this thing so we can see what we actually get. So we're just using the requests library to send that string to NASA and get the results back as a JSON. This is just way nastier than anything you'd want to deal with. It's just a ton of data we don't actually need. So I'm going to suppress that. So under the hood, the CMR URLs function has a filter, and it just pulls out what we need. So it does the same thing, and boom, it just gives us a list of the annual URLs. So Sentinel-1 launched in late 2014. The data started coming down. So basically, we have 2015 through 2020, and the 2021 map will be going online soon. Just a word about the convention here. The 2015 data actually are from December 2014 to November 2015 and so forth with the other years. And the reason we did that was when we aligned the quarterly estimates, it means the summer quarter is June, July, August, if we do it that way, so that 4 quarters fit within this year. It's a little bit of a kludge, but I think it's a logical way to do things. So we're going to load the velocity, and just a quick review of what COGs offer. They put all the metadata at the beginning of the file. A COG is really just a geotiff that someone's thought about how to design it better. TIFF is a very flexible format. In fact, it's originally an image format that then you can actually make into a geotiff, and then you can actually make into a COG if you think about it some more. So typically a geotiff would not have all the metadata at the beginning of the file, especially if it has pyramids. It gets written with the individual pyramids. But instead, what a COG does is it puts all that data at the beginning of the file, so you do one read and you know everything there is to know about the file in terms of where everything is. The data are tiled, so they're stored, which makes for much quicker reading if you're interested in isolated areas. So for example, for 50-kilometer area in Greenland, we don't have to if it was stored line by line raster, there'd be 1,500-kilometer width we would have to download. So 50 kilometers by 1,500 kilometers. But when it's tiled, we only need to just get those little tiles that cover the area of interest. And they also have this nice set of pyramids, which we saw in the last tutorial, and I'll show again here. And then again, we're just taking advantage of all these concepts we've gone through over the last week. X-array, parallel operations from Dask, local and remote subsetting, lazy opens, and subsets can easily be saved for later use. So before we create our velocity stack, we just need to condition the file names a little bit. We did the search up here and we got back, it's set up to return the VV, which is the speed of the glacier, but there's also a VX, VY, and there's actually error components too, which I'm not going to cover today, but this should all work with the error components if you specify them properly. And so instead of that VV, we just swap it out and put in a wildcard character there. So that's what this step is doing. And I also strip off the TIFF file name because this is sort of a pattern, and the TIFF, or some of the code could actually handle the shape file. So we just don't put we have the code itself append the appropriate file extension. So we do that, and boom, we get another one of these nice Rio X-array graphical descriptions of the data. So you can see Greenland is a smaller image than we looked at earlier. That's because it's a 200-meter data set for the velocity, not a 25-meter data set like we were looking at before. But we also have this three bands deep, so VX, VY, and VV. And actually, I should just note this. We use this read speed equals false here, which means it just it only read VX and VY because it can actually compute the speed faster than it can download it. So we would have got the same result either way, just download it a little bit more quickly. And everything is stored in this X-array that we're looking at. And in this case, again, it's 6 levels deep in time. So it will download in a reasonable period of time. If we wanted to download the whole thing, it would be 7 gigabytes and 370 gigabytes for the whole 6 to 12 day data set. So we're only interested in the area we showed up above. So if you recall, we defined this bounding box here. And now we're going to use that bounding box here, and we're just going to do this subset vel, which you stick in the box and you get your subset. And the full X-array, by the way, is still saved, so we could actually change this subset multiple times. We might have to re-download the subset again, but we could do multiple operations. So now we've got down to 15 megabytes, which is, again, going to download much more quickly than 6 or 7. And as I mentioned before, we can either wait till Dask decides it's time to load that usually works pretty well. Once in a while, if you actually try and like look at a value or something, it's a pain because you get back a Dask array number, which then you have to do the compute. So often it's just nicer to download the data, especially when it happens quickly. Okay. And as with the other data, it's nice to have an overview image. So here we're going to use overview level 3. And we don't actually need a stack of overview images if we just want to say inset map. So we're actually just going to pull the one. Boom. So instead of whatever it was, 7,000 by nearly 14,000, we just got a little image of the data there. So in the next cell, we're going to actually put it all together and visualize the data and the flow lines. So we're going to display the speed, and I'm going to use it's set up. You can choose. So there's a lot of stuff in this object that's mostly matplotlib stuff to basically give you a nice looking plot right off the bat without having to mess around with it. There's often still a little bit of messing around. And if the nice thing about matplotlib is if you don't like the way I've structured things, you can grab the axis and usually make it look however you would like in terms of font sizes and various things. So we're going to use the overview for an inset, and we're going to plot the flow line locations. And for a later plot, this flow lines object is able to extract a point at 10 kilometers along each flow line. And we're just going to save those for later use. So I'll run this. And so we're plotting the same data twice, once with a linear scale that saturates at 2,000 meters to give a little bit of detail of the slow moving ice. It's a problem with things like Jakobshavn. You've got orders of magnitude difference in velocity. So we actually often plot it with this linear log, log scale that uses the color representation here. I've had reviewers complain this might not be good for the colorblind, but I've actually run this through a colorblind filter, and it for the purposes of a map, it actually works quite well. The red actually it's a truncated wheel, so there's not as much red in there as it looks, and it actually looks pretty good through the standard color checkers. And I've just illustrated a few things here. You can plot, if you want, you can do meters, you can do kilometers, you can give the central date of the image, or you can give the date range the image covers, all sorts of things like that. And you can see we're able to plot the flow lines, and there's a little bit of matplotlib stuff here to make the legends so that the flow lines didn't get doubled up and repeated. But it's all fairly straightforward, even though it takes up a bit of space on the cell there. So once we have the data, you may want to interpolate it, and we just use the basically it's doing X-array interp function. And so we get this is passing in the coordinates from the flow lines, and I can pass it in as kilometers. As long as I tell it to expect kilometers, I can pass it in as meters if I tell it to expect meters. This will look familiar if you saw Tyler's spatial transform talk. So here I've actually just converted the XY coordinates into lat long for the purposes of demonstration. So then if I shove them into the velocity object as lat long and tell it expect lat long, it will interpolate. So here are the 3 points interpolated, and you can see, or 3 of the points that were interpolated, and you can see basically they're all exactly the same down to several significant digits, more than you would ever care about, given the errors are the order of a meter or more. Also, you can ask it to return so basically these functions for people who like NumPy array, it can usually return everything as a NumPy array, or for people who'd rather have an X array, you have that option too. So you can get same result as an X array, which I'm going to just suppress. So then we can do some basic plots of and see what's going on Jakobshavn over the last few years. So we're not going to look in this next example. We're only going to look at the central flow line, which is flow line 6. And we're going to make a plot for each glacier. And then we're going to loop over the glacier's ID and the axes. So we've got 2 axes and 2 glaciers. We're going to interpret the points along each, the set of points or the flow line for each glacier. And then we're going to loop over the dates in that. And we're going to plot the results. Get something that looks like this. So you can see that actually the glacier was the slowest. Joughin was slowest in 2018. It picked up a little bit in 2019. It was sort of the fastest in 2015, 2016, and kind of started to slow down in 2017. And this is a well-known slowdown that occurred at this time, and the glacier has since started to speed back up again. And then this glacier is doing a little bit more erratic stuff. It's hard to tell exactly what's going on. So this is nice for sort of getting the spatial picture, but it doesn't necessarily give you the best time thing. You've got to look at colors and figure out what's going on. So we'll just plot the points through time. So this is, if you recall, up here we extracted the point from the glacier at 10 kilometer, and we saved it in this dictionary. So here are our points here. And this time we're going to look at a point from each flow line ID, each flow line for each glacier. So 6 points, 2 glaciers. I'll just generate the plot. And now you can see much better what's going on in time. You can see sort of peak speeds here and this sort of fairly pronounced acceleration. And this was on an annual basis. The summertime accelerations are even more dramatic. But you can see it bottoming out in 2018 and rebounding. And then you can see here, there's sort of some ups and downs on this other glacier. So you may want to work on these data and pull the data down and make a figure like this. And it's great that you can get it directly from NSIDC. But if we were doing, say, the 300 glaciers, again, it might take 5 to 10 minutes to download the data, depending on what your network's like. And you might want to tweak up your plots on the airplane on the way to a conference or something. So we can also save the data. So the Vel series and the image series, I didn't demonstrate it, but it has this save function, and it'll just write it all to a netcdf. And then you can basically, I just read that back in and regenerated the same plot above, just to demonstrate that it can be done. In fact, that complicated plot I showed at the beginning, there was quite a bit of downloading on that, maybe 20 or 30 minutes. So I just saved all of the results and just had an if the saved file exists, work from that. If not, re-download it. And the plot generates very quickly once you saved all the little bits. So to summarize this part of the so we can access stacks of velocity data using these tools. We can display velocity maps and interpolate points or lines, which are the kind of things typically you'd want to do in a glaciological analysis. Again, there's many other data sets that these tools will work for. We can save the data once we downloaded it, and there are more notebooks on the, and we will add with time to the GRIMP notebooks repo. And they can provide context for elevation change measurements. If you're seeing thinning on the glacier, it's either melting or there's some dynamic thinning going on. So you really, and anything that's above more than a meter is going to be largely driven by dynamics, above a meter a year. So you really want to have the velocity data to provide context for those changes. So with that, I'm going to turn it over to Zach, who's going to work on integrating these data with the ICEPICS data.
All right, thanks, Ian. So Does this look good to folks? Just to double check. All right, I'll take that as a yes.
Good, Zach.
Okay, thank you. All right, so as Ian said, we're now going to shift gears back to the ICESat-2 and airborne LiDAR data. If you remember yesterday, we ended on a bit of a cliffhanger, demonstrating that the ICESat-2 and ATM data lined up pretty perfectly. So if you were kind of sweating at the palms, wondering what we were going to do with that data, we're going to take care of that now, basically. So what I'm going to do first is basically rehash what we did yesterday in terms of loading up all of the data. So first we have the ICESat-2 data, which once again, we'll put into these two data frames, load the ATM data into its own data frame, and then do the filtering that we did yesterday, where we're only looking at the nadir tracks and converting the longitudes to be consistent with ICESat-2. So yeah, these files should be in the folder. If they're not, then you can run yesterday's tutorial in order to get those files again. But I think I already pre-downloaded them into the repo. Anyway, so we've done that. We're going to once again subset the ICESat-2 data using pandas-based slicing. And what we're going to do now is do some along track surface height. Just do a plot of along track surface height, because as we saw, the two LiDARs seem to line up very well with each other. So if I run this, we get a basic along track plot with latitude on the x-axis and elevation on the y-axis. We have the weak beam of ICESat-2 in blue, the strong beam in orange, and ATM in green. And what we can see right away is that, sure enough, the strong beam and ATM actually match up really well. There is a little bit of variability with the ICESat track that might just be a consequence of some rough topography in the area, but otherwise it actually looks really good. And so that's great. So what we can do now is just do like a very basic bias assessment between these two beams. So what I'm going to do now is I'm going to downscale the ICESat-2 data to be equal in size to the ATM data just by using a simple spline interpolation from SciPy. And once I do that, I'm going to calculate the bias between the two simply by taking the difference between the ATM height estimates and the ICESat-2 height estimates. So once I do all of that and then plot it onto Matplotlib again, then we get this very basic plot for bias along track. You can see that it's pretty jaggedy, kind of goes alongside all of that variability that we see in the ICESat-2 track. But you do see that it is generally within about 5 to 10 meters, sorry. And then the mean bias generally is about 33 centimeters, which isn't too bad. And you could probably attribute some of that to, again, some of the rough topography in the area. So that's just one thing that we could do with this data, and it's pretty neat. So now what we're going to do is combine the ATM data with some of the ice velocity data that Ian was talking about. We're doing this because ATM actually has a pretty extensive library going back to about 2011 over Joughin. So that means we can derive some surface height estimates over Joughin and just see how they change with each year. There's a lot of stuff going on here, but the gist is that we're going to look at all the ATM tracks from 2011 through 2018, and all of this data is included in a CSV file that I have downloaded on the repo. Essentially, this file is just a combination of ATM files that I just compiled ahead of time so that we didn't have to go through all of that during this tutorial. And so we're going to plot that alongside the ice velocities. So if I run this cell, so these two plots should look a little bit familiar, the left and right ones. We have the mosaic of ice velocity right here, and then the along track estimates of ice velocity for 2015, 2016, and 2018. And then here in the middle, we have the ATM ice height, the along track ATM ice heights for 2011 through 2018. So as Ian was alluding to, once again, we can see that that there is a pronounced decrease in the ice velocity in 2018. And while we do see a pronounced loss of ice after 2011, it's a little hard to like properly parse out what's going on in 2018 through just this plot alone. Like it looks cool, but it'd be nice if we had something just to give us a better idea of what's happening. So what I'm going to do now is I'm going to zoom into this area right here, because that's where there was the best data coverage in 2018 for ATM. And I'm going to derive some basic surface height, like mean surface height estimates over the region. And then we're going to basically derive a time series of ice loss. So there's a lot of code here, but the gist is that we're going to take the 2011 data, which is right here, and we're going to find the mean height at 2011, and then we're going to find the mean height at every other year, and then take a difference relative to 2011. And then we're going to plot that as a time series. So if I do that, we get something that looks like this. So here's 2011. Obviously, there's no change relative to itself, but then between 2011 and 2013, there was a pretty significant loss of ice heights, which makes sense. 2012 was a pretty big melt year. And then we see a gradual decrease down to 2016. And then interestingly enough, we seem to have some accumulation that increases the ice height in 2018. And that seems to correspond with this, with the ice velocity drop. So that's a potentially interesting result right there. All right, so we've now looked at an ATM time series. Now we're going to try and do the same thing for ICESat-2. Since there's only a couple of years worth of ICESat-2 data, there's not going to be quite as dense of a profile. So just keep that in mind. But what we're going to do for this is that we're going to, once again, turn to IcePix to download this data for us. This is fairly similar to what I covered yesterday, but there are a couple of important differences. For starters, instead of using the KML, ignore this comment right here, I'm using these lat lon bounds just to save us some time and keep us within those bounds, just to keep us within that along track pattern that we had with ATM. And instead of looking at just April 2019, I'm extending the date range to December 2021. But then we're still going to keep the same RGT just so that we can see how the ice heights over that RGT change over time. So we'll run that cell and then set up our query object once again. And once we check out how many granules we have, we can see that we have about 11 or 12 data files we look at. So that's a fair number. So once we actually order the data, it might take a little bit, just as a heads up. So I'll just go ahead and run this. And sure enough, it's being a little choosy at the moment. While that's going, I'll just go ahead and note that we have this path variable that refers to a temporary file, to a temp folder, I should say. So make sure that you have this path right here. And it's important that you also make sure that this line right here notes that temp folder. The copy of this notebook that is in the repo might not have this temp/data integration. So if it's not there, then go ahead and add that, and hopefully this cell should run for you. Okay, so looks like our granules have been ordered. You can see that a couple of granules don't have any data available, and that is most likely because there's clouds over the region at that time. And so moving forward, I'll just note that we do have a cloud filter just in the event that they get in the way. Anyway, so I'm going to download these files, and they should be in the temporary folder now. And then now I'm going to try and derive the along track surface heights for these 11 data files. So again, I'm going to do latitude on the x-axis and elevation on the y-axis. And in addition to that, I'm going to apply a cloud filter because Joughin can be a pretty cloudy place. And they can get in the way sometimes. So we're going to just check and make sure that we're going to look at this cloud flag. And if it's less than 2, then that usually means that you're looking at a relatively cloud-free environment, or most likely are. And if it's higher than that, then it's probably going to be cloudy. So we're just going to say that there's no data there, or it's some rather unreliable data there. So we do this and we plot it, and we should get something that looks like this. As you can see, it looks a little bit messier just because it's probably capturing more of those surface features that are in the Joughin region. And you can see that we did lose a fair number of files because of cloudy scenes, but we do have, I would say that we have enough to derive just like a very basic and simple time series over Joughin. So we'll do that, and we'll make the ice height change plot relative to April 2019. So if we do that, we get something that looks a little bit like this. Again, we see like a general decrease in the ice height trend. We do have quite a bit of spread that seems to correspond with the jagged nature of some of these plots. So that's fairly understandable, but otherwise it's a fairly interesting result. And through this, we were actually able to use both the ICESat-2 and this airborne LiDAR data to see how the ice changes over the course of several years. So with that basically covers everything. So thank you, everybody, and we'll be around for any questions that you have.